Hi, I'm going to take a look at the practicalities of using freeRTOS and compare it to a simple implementation of a task scheduler. I'm going to start out by looking at and building and running the freeRTOS example project with the Raspberry Pi Pico. So here is the freeRTOS example. We have a CMakes list and then a subdirectory with the actual C file in here. So first things first, if we look at the CMakes list, we have this environment variable here that the CMake file is checking for. That points towards the freeRTOS SDK. So hop on to the internet and go over to freeRTOS.org. Once you've downloaded the SDK, unzip it, and then in here we have different flavors and different libraries. What you want your environment variable to point to will be the freeRTOS kernel. So here I have my variable freeRTOS kernel, and I merely put it in my bash rc file. So once you've got an environment variable pointing towards freeRTOS SDK, you can move on with building project. Make the build cd build cmake ... configuration done, and then call make. Give it a while. We've built the executables. If we look at the build folder, we have this hello freeRTOS as defined in our CMake file, freeRTOS hello. And so if we go in here, we have all of the built files. So I'm just going to put the Raspberry Pi Pico into bootloader mode. Okay, so the firmware has been moved onto the device. Now if I open up a terminal, we can see a bunch of printfs from tasks that are executing. So let's look at the source code. Now the source code does look a bit daunting with all of these macro statements. However, as with everything, once you slowly work your way through it, it makes sense. Depending on this variable here, which is actually defined in the CMake file, it is either going to run on one core or two cores. Got the main, setting everything up, init, multi-core launch, and then we've got this key function here, xtask create, and we're creating a main thread, and the main thread is printing out this statement, hello from main task, and then we have a worker as well. Now to get started with freeRTOS, we can go over to their website where we will find some very good documentation. We have a beginner's guide with some fundamentals. So here we've got a very nice, easy to understand diagram of how the time slicing works in freeRTOS. Now, one of the strengths of freeRTOS is its maturity. There's a vast array of devices that are supported by freeRTOS. And because of its maturity, you will quite likely find an example freeRTOS project for any device that you choose to work with. The API reference. Here we've got xtask create. So let's see what this function does. Create a new task and add it to the list of tasks. And here we've got a pointer to the entry function, a descriptive name for the task, the number of words, not bytes, to allocate for use as the task stack, parameters, a value that is passed as a parameter to the created task, and priority and px created task used to pass a handle to the created task, and all the other key functions and functionality and variables are documented here. So what I'm going to do is I'm going to modify this project and I'm going to use a queue. Here is my modified project. What I have done is I've created a couple of queue objects. If we go to the documentation, create queue, we've got creates a queue and returns a handle by which the queue can be referenced. We've got the first parameter is the maximum number of items in the queue, and the second item is the size in bytes for each of the items in the queue. I've got a queue the size of 10, and each item in the queue is a unsigned 32-bit int. And in my main task, I have a counter that I am incrementing, and then I am sending that to the other task using this function xQsend. We've got post an item on a queue. First parameter is the handle to the queue. We have a pointer to the item to be placed on the queue. Then we have the number of ticks to wait, the maximum amount of time the task should block wait for space to become available on the queue. Then I am reading the queue associated with this task to see if the other task has sent an item onto the queue using this function queueReceive. We have receive an item from the queue. The item is received by copy, so a buffer of adequate size must be provided. So the first parameter is the handle of the queue. The second item is a pointer to receive the item that you are reading from the queue. And then the final parameter is the number of ticks, the maximum amount of time the task should block wait for an item to receive should the queue be empty. By setting it to 0 will cause the function to return immediately if the queue is empty, and that is what I have done here. And I'm calling it in a while loop because this task is running at a different frequency to the other task, which means that data in each of the queues will fill up at different rates. So now let me build and run this project. Now open a terminal. We've got the main task printing out its counter. Within the loop, we are printing out the counter values received from the other task. One of the main drawbacks of freeRTOS is the overhead. So there's the learning curve of learning the API, but then also there's the ROM and RAM that is associated with the framework. So for example, I've just got a simple multi-core project running 3 tasks and a couple of queues to pass data. And if we look at the built project, it's 102 kilobytes, which is quite sizable for such a simple project. Now, thinking about the large overhead of freeRTOS, a project called ThreadX came to my attention, which boasts being able to have a minimal size on a ARM architecture processor. Okay, so this is the repository for the project, and if we go to support, we have a list of supported architectures. Now, configuring ThreadX is a bit beyond me, but someone has a project where they have configured it to run on the Raspberry Pi Pico. So I'm going to clone, build, and run this, and then load the firmware onto the device and run a terminal. Demo ThreadX. We see that thread 0 is printing out the data. Then we've got a thread 1 and we've got a function txqsend, which is very similar to the function in freeRTOS. And here we've got another thread. This one has a receive function, again very similar. And then we've got some interaction with a semaphore. So there's very similar functions to those that were seen in freeRTOS. One question you need to ask yourself is an RTOS even really needed? Using a simple task scheduler is actually a fairly effective solution for managing a moderately complex project. Here I've got a simple task scheduler project. I've got a strut that includes a function pointer, an ID, a deadline, and a timestamp. And then in a loop, we simply check to see if the deadline has expired. If it has, we then call the function pointer and update the timestamp. And then you could either idle the processor or you can work out the remaining time in a time slot and make the processor go into a sleep. In this implementation, I included an ID, which means that you can easily delete the task, and it also means that you can store associated data to a task. I am inserting data into a map. Then in my tasks, I am retrieving any data associated with that task. So I'm going to build and run this. So each task is being called as per the deadline given to the task in the initialization. The associated data with task 1 is data A. Task 1, data A. In conclusion, a simple task scheduler is quite adequate to deal with a moderately complex project. Where freeRTOS really comes into its own is its ability to efficiently utilize multi-cores and to handle task prioritization. For a complex project on a multi-core MCU, I would definitely recommend using freeRTOS.